We're going to finish up this topic of first order circuits analysis with just a couple more examples. This first example is shown on my notepad, where we have a switch, a multi-position switch that changes from position 1 to position 2 as shown in the diagram at t equal to 0. So we want to find what the current through the 23k ohm resistor is just after the switch changes from position 1 to position 2. And then also we're told that while the switch is in position 1, it's been there for a long time, so it has reached steady state before the switch changes from position 1 to position 2. So to do a problem like this, you first analyze a steady state circuit with the switch in position 1, and then you do a t equal to 0 plus type of analysis, an initial condition analysis, once the switch is changed to position 2. So we first look at this circuit here where the switch is in position 1, and since the capacitor is initially uncharged, we represent the steady state condition of that capacitor as an open. So this open right here is the steady state condition of the capacitor. And now we want to find what the voltage across that open is, right? Because if we find the voltage across the open, that's the steady state voltage of the capacitor. Okay, and that will be significant. That will, be something that we need to know in order to determine the current through the 23k ohm resistor when the switch changes to position 2. So this just becomes a node voltage analysis. Okay, we just need to get the voltage on both sides of the open, and that will give us the voltage across the open. The difference will give us the voltage across the open. So VA, okay, we know that at this node right here, there's 130 volts. And at this node right here, there's 130 volts with respect to ground. And since there's no current flowing through this 7K, there's 0 volts across it. And anytime you have 0 volts across an element, that means the voltage is the same on both sides. So 130 volts on this side with respect to ground. There's also 130 volts at node A with respect to ground. Okay, then VB. VB is the voltage at this node, and it's the same argument that no current through this resistor, so 0 volts across it, so you get the same voltage on both sides, so VB is just 35 volts. And now the voltage across the open is just the difference of 130 minus 35, which equals 95 volts. And the polarity of that 95 volts would be that the higher voltage end is this end, node A, because 130 of course is greater than 35. Okay, so now we know that the capacitor will charge up to 95 volts. So when the switch is changed from position 1 to position 2, this is our circuit. This is now our initial condition circuit to find this current. Okay, we want to find the current through the 23k ohm at this time. Well, as we talked about before, when you have a charged capacitor, we represent that charged capacitor at the initial condition as a voltage source of value of whatever voltage it charged up to. So you see this 95 volt source, that's the capacitor that we found the voltage for just a moment ago. Okay, so now it just again becomes a circuit problem where we just need to find the current that's flowing in this path. This is all in series, so we can do a KVL. When you do a KVL, these two voltages here are going to oppose each other because of their polarities being opposite. So the current that's flowing in this path, okay, which is the same current as the current through that 23k ohm resistor, it's just going to be 130 minus 95, and then divided by the total resistance in the path. So we just add up the two resistors since they're in series. 30k ohms. So 35 volts divided by 30k ohms, that comes out to a current of 1.167 milliamps. Okay, so that's our answer. Okay, let's do one more problem. Okay, here's a problem where we have an inductor and the switch is closed before t equal to 0, and then at t equal to 0 the switch opens, and we're told that the current through the inductor is 1.7 milliamps before the switch is open. So again, you're assuming here that you have steady state before the switch changes. So you see that 1.7 milliamps, that's the steady state current through the inductor before the switch changes from a short to an open. And in this problem we want to find what the voltage across this resistor is just after the switch is open. Okay, so this is very similar to the problem we just finished, but here we don't have to do a steady state analysis because essentially the problem statement gave us the steady state before the switch changed. So to find the voltage across the 3K, okay, we just find the voltage across the 3K just after the switch changes position. Well, we look at our t equal to 0 plus circuit. So everything over here, the source and that switch, I didn't draw because since the switch is open over here, all this part of the circuit is not connected. So all we're left with is what you see here, and the key point is that with inductors, it's current that can't change instantaneously. So whatever current that inductor had right before the switch changed, it's going to have the same current just after. Okay, in the previous problem we had a capacitor, and with capacitors it's the voltage that doesn't change abruptly. So that's why once we found that there was 95 volts across that capacitor before the switch changed from position 1 to position 2, well, it still had 95 volts across it just after the switch changed to position 2, and that's why we represented that capacitor with the 95 volt voltage source. Okay, but here we have an inductor, so its initial condition when it's initially energized is that of a current source with value of whatever current that it was energized to, which again in this case was 1.7 milliamps. Okay, so once we have our initial condition circuit here, again this just becomes a problem like those that we had solved earlier in the quarter. And what I did here is I used a current divider to find what the current through the 3K is. Okay, because see these two resistors, the 6Ks, they're in series, and those two 6Ks in series are in parallel with this 3K. So using current divider to find the current through the 3K, okay, current divider equation would look like this. You'd have 3K in parallel with 12K, and then 3K in the bottom. This here, if you do product over sum with 3K and 12K, you get 2.4K. So this comes out to 1.36 milliamps. And now the voltage across the 3K would just be the resistance of the 3K times 1.36, and that's a voltage of 4.08 volts. And if you wanted to put the polarity would be on the bottom side here, because the current's going to flow into this bottom node and then up through the 3K. And again, as we've seen many times, the higher end voltage for resistor is always where the current enters the resistor. Alright, so this finishes up the topic of first order transient analysis. And now, for the rest of the quarter, we'll be analyzing AC circuits. So we'll start AC circuits in the next video.